सर आज लास्ट टॉपिक है
जी बेटा लास्ट टॉपिक है दिस फॉर दिस पार्ट ऑफ द कोर्स. नेक्स्ट वीक डॉक्टर Burhan will take your classes. Okay, Bismillahirrahmanirrahim. Can you see the slide? Earthquake resistant design. Earthquake resistant.
Yes, sir.
Slide nazar aa rahi hai. Good. Okay, then we can start. There can be three different types of the earthquake. Shaking of the earthquake can be minor, it can be moderate, it can be severe. What is a minor earthquake? During the minor earthquake, there should not be any damage to the structural and the non-structural components. During a moderate earthquake, there can be small damage to the structural components and some damage to the. Okay, this one we'll discuss later. So we have three types. Either the earthquake is minor, moderate, or the severe. Okay. Then, what should be the design philosophy for the design of the earthquake? Should we do away with the design of the buildings? For the earthquake effect, we design the structure only for the gravity loads. We don't consider the earthquake loading. This is one extreme. The other extreme is we can make our structures earthquake proof. We can design our structures for the severe earthquake. Either you forego, you don't consider the earthquake loads altogether, or you can make your structures earthquake proof. So these are the two extremes. So as a structural engineer, which approach you will use? You will try to make your structure earthquake proof, or it can be without any seismic provisions. उसके बगैर करना है, earthquake effect को consider करने के बगैर करना है, or you will try to make it earthquake proof.
Sir, it depends on the location.
Depends on the location. क्यों location पे depend क्यों करता है बेटा?
सर सीस्मिक एरिया होगा तो सीस्मिक के लिहाज से करेंगे.
Okay.
अगर सर सीस्मिक ना होगा तो माइनर अर्थक्वेक हम भी डिजाइन कर सकते हैं.
We have already seen that the chances of the probability of occurrence of the large earthquake is very rare, very small. Okay, maybe one time in 100 years or one time in 200 years. ठीक है ना? For a very large earthquake. So definitely it depends where you have to design the structure. Suppose you have to design the structure in the area where the chances of the occurrence of the severe earthquake is 1 in 50 years.
सर फिर भी स्फीयर कंडीशन पे डिजाइन नहीं करेंगे हम, क्योंकि बिल्डिंग की सर लाइफ इतनी नहीं होती.
हाँ, लाइफ इतनी होती है, ये भी आपका फैक्टर है. If you will try to make the structure earthquake proof, your structure will be very, very costly. यही होगा ना? Chances of occurrence of earthquake is very less.
Yes, sir.
And if you have to make it earthquake proof for the very severe earthquake, your structure will be very costly. So what is the design philosophy? Design philosophy is somewhere in between. You have to design your structure that will be safe during the minor and the major earthquakes, minor and the moderate earthquakes. And if there is a severe earthquake, then you can allow the damage, collapse of the structure or damage to the structure. You can allow some damages to the different components, but there should not be total collapse. You have to save the life and the property which is adjoining to the building. So this should be the behavior during the minor earthquake. You can allow, there should not be any damage to the structures during the minor earthquake. During the moderate earthquakes, you may allow some damages to the structural components, but those damages should be repairable. And during the severe earthquake, you may allow the damages to the structure, but there should not be the total collapse of the structure. In any case, you have to save the lives. So this is a design philosophy. So design philosophy is somewhere between these two extremes. If you will make our structures earthquake proof, that will be very costly. And if you will not consider the earthquake loads, then even during the minor or the moderate earthquakes, your structure can damage. So it is somewhere in between. It is very difficult to predict the future earthquake. So what we will do for the design of structure, we will use the experience which we have from the past, experience of the behavior of the similar structures in the past. So we will use the reasonable and the prudent practices to keep our structure safe during the earthquake, during the future earthquake. We have seen in the past that the structures, they lack their basic resistance to the earthquake. So we will use the good building construction practices. So the rule is simple. We cannot prevent the damages during the moderate and the large earthquake, but we should have to save the lives. It should not be life-threatening collapse, and there should not be total collapse of the structure. And we can allow the damages which are repairable, especially during the moderate earthquake. Buildings are not designed for the full earthquake forces. They should have the sufficient initial stiffness and the ductility, so they can respond. They should not be total collapse of the structure. There should be only the local damages, local failures, which we can repair. So we have to make the balance between the cost and the acceptable damage. They should be. We can reduce the cost with the acceptable damage. And how can we design the structure which are economical and the damage is within the acceptable range? We have to get the guidance from the seismic codes. The wealth of the information is given in the seismic code, in the precise seismic design provisions. So we have to follow the code. And our design philosophy is that our structures will be earthquake resistant, not the earthquake proof. So we have to make our structure earthquake resistant, not the earthquake proof. What is the initial stiffness? Stiffness of the building within the elastic range. This is the slope of the curve at this is the initial stiffness. It should be high. The structure should have enough strength, and at the same time, they should be ductile. What is the ductility? This is the area between under the load deflection curve, or it is the ratio of the maximum displacement to the displacement at yielding. So your structure should have the lateral stiffness. It should have the sufficient strength, and the structure should be ductile. And you can see the failure of the different types of the structure. If the structure is brittle, it will collapse without giving any warning. And if the structure is ductile, it give you some warning before failure. So you will try to design your structure which are ductile, which has sufficient initial stiffness and the strength. They should not fail in a brittle manner. So in the brittle manner, if they will fail, they will be the collapse of the structure. Okay, hazard, and then we have the vulnerability. In our case, hazard is the earthquake, and we have the vulnerable structures. Because of a certain earthquake, because of the occurrence of the earthquake, the structures can damage. So this disaster, because of the earthquake, it is a function of the occurrence of the earthquake and the structures which may damage. So this is the vulnerability. So hazard, disaster is the function of hazard and the vulnerability. And after the disaster can happen, you can see there will be damages. And then hazard into vulnerability. This is a disaster minus the capacity of the structure. That is the risk. If the structure will have more capacity for that disaster, the risk will be less. If the capacity is less, then the risk will be more. How can we reduce how can we prevent and mitigate the disaster? For example, if there is some earthquake and our structures are properly designed, we can reduce the risk. They have some capacity to resist that particular earthquake. Can we prevent the disaster? Earthquake is not in our control. How can we prevent the disaster? Any student? Disaster को prevent किस तरह कर सकते हैं?
Capacity increase करके.
We can increase the capacity. We can design our structures which will be earthquake proof, but that will be very costly. So normally we mitigate the risk, okay, instead of preventing the risk. We cannot prevent the risk. That will be very costly solution. But we can increase the capacity and we can mitigate the risk. And whenever there is a disaster, we have to be prepared for the similar disaster in future. And we have to take some precautionary measures. And this is the procedure for the disaster preparedness. If there is some disaster, what is the immediate response? You have to secure yourself and the others. And then you have to provide the relief to the affected peoples. You have to provide the food, shelter, water, sanitation, clothes, medicals to the peoples which are affected because of that disaster. And this is a short-term solution. Then you will have rehabilitate the facilities. It will take say weeks and months, and then you will reconstruct the facilities. It may take some years. And then you have to prepare for the future disaster of similar nature. You can plan, you can give the warning, you can, in case of the earthquake, you can prepare the hazard maps, you can check the structures, and you can strengthen the structures so that disaster will be less. You can increase the capacity of the structure. Okay, so you can prepare for the future disaster. So this is the procedure. Look at here. Look, earthquake do not kill peoples. Improperly designed structures do. Because disaster is the function of hazard and the vulnerability. Earthquake is not in our control. But we can design the structures in such a way so that they cannot cause the damage to the life. So they should not fail. They should not fail in a brittle manner. They should not collapse. So that earthquake, it do not kill the peoples. In properly designed structures, they kill the peoples. To design the structures for the earthquake loading, the important parameter is the time period of the structures. So you should have an idea, rough idea about the time period of the different types of the structures. In this slide, the time period of different types of the structures are given. For example, if it's a single story building, time period is close to 1 second, 0.05 to 1 second. For the low rise building, 4 to 5 stories, time period can be 0.4 second to 5 second. For the high rise building, we have the rough formulas, empirical formulas we can calculate, but the rough idea is time period will be equal to number of stories divided by 10. For the reinforced concrete chimney, time period may be close to 2 seconds. For the elevated time, that time period is more 4 seconds. Suspension bridges, time period is more 6 seconds, 6-7 seconds. And for the large gravity dams, time period is very short, that is less than 1 second. So you should have an idea about the time period of the different types of the structures. You can see from this slide. Okay, now I have one question. We have the different height buildings here. So what do you think during an earthquake, the shaking of these buildings or the vibration of these buildings will be same during that particular earthquake?
No, sir.
Sabki shaking same hogi?
It will be different, sir.
It will be different. It depends on the
Mass.
Natural
frequency of structures.
Actually, it depends on the time period or the frequency. Okay? It depends on the stiffness and the mass both. K over M ratio, not only the stiffness, not only on the mass. So time period is different, angular frequency is different. So these are the frequency contents of the earthquake. We can transform the seismogram into the frequency and by using the Fourier series, and we have the frequency content of the earthquake. And definitely if the frequency of the dynamic loading is close to the natural time period of the frequency of the structure, it will be more damage than the other structures. The vibration response or the amplitude is the function of omega to omega n, R ratio. So some structure will shaken more than the other structures. These are the principles for the earthquake resistant design, and these principles are very important. First principle is the architect and the engineer should collaborate from the outset. What is the role of the architect? Architect करता क्या है? What is the role of the architect and what is the role of the structural engineer?
Sir, architect
Architect.
shapes members के
Give you
shapes
the
वगैरह
conceptual
बनाता है.
design, architectural design. ये होता है ना? Architect will decide about the architectural features, not about the structural components. And once the architect will finalize the architectural component, or it will finalize the conceptual design. Normally, the routine is structural design, then check. A structural engineer then check and decide about the different sizes of the different components. Materials sometimes he change about the foundation. So that is the serial design. Once the design is finalized by the architect, then the structural design is done by the engineer. That is a bad practice. Good practice is that architect and the structural engineer, they should collaborate right from the beginning. So they have to develop safe, efficient, and economical design that can resist the gravity loads and also the seismic loads. So during the conceptual stage, you should collaborate with the architect, not that will be the parallel design. Okay, so is architect and the engineer should collaborate right from the beginning, not architect finalize the design and then the structural engineer do his job. This is the first practice, first principle. Second principle, we have the different kinds of the codes. Seismic provisions are given in these codes. We have the international codes and the national codes. You can see here ISO code, International Building Code, Uniform Building Code, Euro code. And in Pakistan, we have the Building Code of Pakistan. We have the seismic provisions there. So we have to follow these codes fully, not partially. Okay. So this is in the vested interest of the owner, architect, and the engineer to follow the codes, and that should be the part of the construction documents. Okay, the configuration of the building is very important to resist the earthquake loading. And look at the statement given by late Henry. If we have a poor configuration to start with, all the engineer can do is to provide the bandit. Configuration is poor, and even the experienced engineer cannot improve its performance. He can only provide the bandit, or in other words, he will give the solution which will be costly. Okay, if the configuration is poor. On the other hand, if the configuration of the structure is very good, framing system is good, then even a poor engineer having very less experience, that cannot harm the ultimate performance of the structures too much. So the configuration is good. Even the experienced engineer cannot do anything. He can only make that structure earthquake resistant, but that will be costly solution. But if the configuration is good, then no need to do a lot of calculations, rigorous calculations, because the performance will not be affected too much. That will be the earthquake resistance automatically. So configuration of the structure is very, very important. What should be the configuration? Let's see that it should not be too tall and large in height to base ratio. If it is too tall, then latent displacement will be more. It should not be too long and too large in plan. If it will be too long or too large in plan, then it can attract more inertial forces. Damages will be more. So it should not be too tall, too long, and too large in plan. Then it should be simple. It should have a simple plan. If the building is simple, no need to worry. I have some disturbance. किसी का mic on है? जी बेटा. Roll number 191. कर दिया बेटा आपने?
सर रिमूव कर
यस
दें?
सर।
नहीं, रिमूव नहीं करना।
सर वो
माइक
पता नहीं था चला आना।
चल, इट्स ओके, नो प्रॉब्लम. Okay, the building should be simple in plan. It should not have the reentrant corners. For example, U-shaped building, V-shaped building, H-shaped building, like these. Okay, they are not they are poor to resist the earthquake loads. Similarly, if we have to, if the architect insists that the building shape should will not be simple, then what we can do? We can separate the blocks. We can provide the seismic joint. For example, here we have L-shaped building. We can provide a seismic joint here that can be properly designed. So it should be simple in plan. If it is simple in plan, then it can resist the loads. It should not have the reentrant corners like here. Performance of these kind of structures during earthquake is poor. There will be damages at the corners. Then soft story. We should have to avoid the soft story. What is the soft story? If the height of the story is less than, if height of a particular story is less than 15%, it's more than the 15% than the other stories. That story will be the soft story. If we have 30% less columns in one story than the other story, that story will be the soft story. Similarly, if we have 30% less full height structural or the partition walls in a particular story, that story will be the soft story. If the lateral stiffness of a particular story is less than 30% less than the other stories, that story will be the soft story. So this kind of irregularity normally it is found in the first story. You can see for the parking purposes, we provide the first story as a soft story. So there is a failure of the soft story in the past because of the earthquake. The lateral stiffness of this story is less than the other stories. So this should be avoided. Not only in the ground, at the ground, but in the intermediate floors. If we have the soft story in the intermediate floors, that can also fail during the earthquake. The stiffness of this story is less than the other stories. So you can see the failure of the intermediate story, that was the soft story. Similarly, these are the failures of the soft story, collapse of the soft story. Then we also should have to avoid the vertical setbacks. You can see here, lower portion have more stiffness than the upper portion. So this is a vertical setback at the level of the change. Okay, there is the sudden change in the earthquake forces. So this kind of setbacks that should be avoided. So vertical setbacks should also be avoided. Okay, okay. We should have to also ensure that there should not be any twisting of the building. When the building can twist, one part of the building is lighter or lighter than the other part. One part is heavier, one part is lighter. We may use this portion of the building maybe for the warehouse. We may have the heavy machineries. So if this portion is heavier than the other portion, you can understand from this example. If this kid is sitting at the corner of the swing, then this swing can twist. Similarly, during an earthquake, the heavier portion can twist along with the horizontal movement. So there will be torsion, and because of torsion, the damages will increase. Similarly, if we have more columns, heavier components on one side of the structure, then on the other side, you can see here we have the wall here, but on the other side we may have the lighter columns. Again, this building can twist. This building can also twist. We have the wall here. On the other side, we have the lighter columns. An example is if the length of the ropes are different. Again, this swing can twist. So if the building is on a slope, length of some columns is different from the other columns, smaller than the other columns. Just like From this example, length of the rope is different. This building can twist, and twisting can cause more damage. This should be avoided in the structure. We may have the prop cantilever overhang building, portion of the building. There is no partition wall here. This building can also twist. Look at this example. We may have the shear wall here. This part of the building, and this part is heavier than the other part. On the other side, we have the lighter columns. This building can also twist. What we can do, if we have to provide this opening and the shear walls, then what we can do, we can place the similar shear wall on the other side. If we have to provide the lift here for going up and down. So for going up, we can have the lift here on one side. We can place the second part of the lift on the other side. So we can place it symmetrically so that they should not be twisting in the structure. Then a practical way for describing the failure of the structure is that we use the concept of weak beam, strong column. It does not mean that your beam should fail. Even in the elastic range, even during the gravity loads, whenever there will be failure during the moderate or the severe earthquake, then your beam should fail, your column should not fail. Anybody can guess why we can allow the failure of the beam, not the failure of the columns?
सर अगर बीम फेल होता तो एक पर्टिकुलर स्टोरी सिर्फ इफेक्ट होगी अगर कॉलम होता तो
we have a localized failure. Okay, but if the column will fail, it's quite possible your structure will be unstable because of the failure of the column. So columns are more important. So your columns should not fail before the beams. In case of the beam failure, we have the localized failure, but in case of the column failure, your structure will be unstable and it's quite possible it can collapse. So you can see the failure of the columns. The structure will become unstable because of the failure of the columns. So columns should be sufficiently strong. And then we should have to avoid the short columns in the structure. Why? For example, in the same story, we have the long column, we have the short column. The lateral displacement of this story will be the same. So lateral displacement of this short column and long column will be the same. But this one is stiffer. Short column is stiffer. It will attract more earthquake forces. The short column can damage. So we should have to avoid the short column. Short column can be because of the reason when the building is on a slope, when we have the mezzanine floor, we have the short columns. Others are the long columns, and this is a short column. And you can see the failure of the short columns. And we may have the partial infill walls. Again, we have the short columns, and this is the failure of the short columns. Any question up to this point? जी बेटा, कोई क्वेश्चन आपका है?
सर
जी.
Sir, I have a general question about earthquakes. Sir, जिस तरह हम weather forecast कर सकते हैं, क्या हम earthquake को forecast कर सकते हैं या कोई ऐसा instrument है?
We cannot exactly predict the earthquake. Highly unpredictable. Up till now, we are not able to predict the future earthquake.
Okay, sir.
But we can maybe 100% we cannot. But with some confidence level, we can say that in this area, this kind of earthquake may come. But when the earthquake will occur, it's again very difficult.
Okay, sir.
Weather we can predict, but earthquake we cannot predict precisely. We may, on the basis of the active fault, slip rate, and type of the soil, we can say that maybe this kind of earthquake will come in future. But what time, what will be the intensity? It's very difficult. Precisely, we may not. It's a complete science. The scientists can predict with some confidence level, but precisely they cannot. Any other question, beta?
सर
जी
सर हमने जो स्लोप्स पर जो पढ़ा है कि वो अनइक्वल लेंथ नहीं रखनी कॉलम्स की, स्लोप्स पर हम फिर किस तरह मैनेज कर सकते हैं कॉलम्स को?
We can design the column in such a way that we can increase the stiffness. We have to properly
Yes.
design.
Yes sir.
We have to properly design this kind of columns. For example, if we have to design this column for this kind of lateral displacement.
Yes sir.
Whenever you have to design the building or the structure on the slope, you should be very careful. The purpose of sharing these principles with you is that you should not have to blindly design that structure. Whenever we have these kind of irregularities, you should be very careful at that stage. We can design.
Yes sir. Thank you sir.
Ji beta. Any other question? Let's repeat the principle. What was the first principle? I'm not showing you the slide. What was the first principle? Because they are important and you should have to keep in your mind while designing.
Collaboration.
They're more important than the basic the detailed calculations. जी बेटा पहला principle क्या है?
Collaboration between
Collaborate with the
architect.
architect right from the beginning. Conceptual design, you have to participate in the conceptual design. In the for deciding about the structural configuration, you should have to participate. ठीक है? Because architect have different things in his mind. So if architect don't agree with you, you should have to convince the architect that its performance will not be good during the earthquake or the lateral loads. So you can convince him. If he will not be convinced, what you can do? फिर क्या करेंगे? Then you can
बढ़ जाएगी.
Then you can take the owner in the loop and you can ask. You can say to the owner that you can design this structure as the earthquake resistant structure, but that structure will be then costly. ठीक है? Definitely you have to.
सर बट रियलिटी में तो नहीं ऐसा होता.
जी बेटा.
रियलिटी में तो नहीं ऐसा होता.
रियलिटी में बेटा यही तो मैं बता रहा हूँ, रियलिटी में नहीं होता तो आपने करना है. अदरवाइज
स्टार्ट में जब फर्स्ट डिजाइन आर्किटेक्चर देता है वो तो कंसर्न ही नहीं करता किसी इंजीनियर से, वो सिर्फ क्लाइंट से कंसर्न करता है.
That is a wrong practice. But I'm saying that is a wrong practice. So you should have the ability to convince the client and the owner. As a structural engineer, you can, if they will not be convinced, then that will be their responsibility, not your responsibility. अगर वो नहीं मान रहे, then what you can do? You can use the mechanical means. You can use the shear wall. You can provide the bracing, and you can use the dampers. You can use the mechanical means to improve its performance. But then you can tell the client that this option will be costly. This will not be cheap. Preferably, you should have this kind of configuration. ठीक है? आपका रोल जोन से आपने बताना है उसे. ठीक है बेटा? तो अगर आपको आइडिया होगा तो बताएंगे ना आप. जी बेटा. Next step क्या है? Next principle. So it should be the panel design, not the serial design.
follow करें.
We should have to follow the codes. We have the wealth of the information in the seismic codes. So we have to follow these codes fully, not partially. And we have to make the calculations and the verifications of the different provisions as a part of the construction documents. Okay? So follow the seismic codes. Third क्या है?
बिल्डिंग्स काफी ज्यादा हाइटेड ना हो या बहुत ज्यादा वाइड ना हो.
You should have to select the good building configuration. What is a good building configuration? पहला क्या है? It should not be too tall, too long, or too large in plan. दूसरा क्या था? Second configuration. It should not have the soft story. Okay, it should be simple in plan. It should not have the reentrant corners. Okay, but if we have a different type of this, for example, you are L-shaped building, we can separate the different blocks by providing the seismic joints. So plan should be simple. If the plan should be simple, that is that can resist earthquake easily. the capacity will be more to resist the earthquake loads. Okay, the soft story should be avoided. This is very, very important. If the stiffness of a particular story, latest stiffness of a particular story is less than the other stories, that story can fail. You can see here, failure of the first story, ground floor story, intermediate story during an earthquake. Then you also have to avoid the vertical setbacks. Okay, at the level of the setback, there is the sudden change in the earthquake forces. Avoid the twisting. This is very, very important. Okay, so your structure should be placed, it should be symmetrical. If it is heavier on one side, lighter on the other side during an earthquake, it can twist. Twisting can cause more damage. And whenever you have to design the structure on the slope, you should have to be very careful. And when you have the heavier components on one side, lighter components on the other side, again, you should be very careful while designing. You can increase the stiffness of these columns, or you can partially provide, you can increase the stiffness on the other side. Again, this building is unsymmetrical. It can twist. Okay, this is very important. You have to use the concept of strong columns, weak beams. Your structure, your column should not fail in any case. If there is a failure of the column, there is the structure may be unstable. So that is not acceptable. But if there is a failure of the beam, then there will be a localized type of failure. You can see the failure of the columns. Structure may become unstable. And if we have the short columns, they should be avoided. And if we have to design the structure, how can we avoid here? We can redesign. We can not have to provide the mezzanine floors. Okay. And if we have to provide the mezzanine floors, then we will be very careful about this portion of the design. Similarly, we have partial infill. We have the short columns. They can fail. For the openings, we can provide, but that partial infill should be avoided. Okay. If your configuration of the building is not good, then what we can do? How can we increase the load carrying capacity of the structure, earthquake load carrying capacity of the structure? We can use different means, mechanical means. We can use the shear walls in the structure. We can provide the bracing in the structures. We can use the dampers in the structures. And also we can use the base isolators. So what are the shear walls, cross bracings, dampers, and the base isolator? One by one we will discuss. Shear wall is simply a vertically oriented wide beams. Cantilever wide beams, vertically oriented wide beams that carry the earthquake loads to the foundation. One of the eminent consulting engineers in the USA, he said that we cannot afford to build the structures, concrete buildings, to resist the severe earthquake without the shear walls. So in the high seismic zone, we should have to provide this shear walls. We cannot design the structures without the shear walls. And how should we have to place the shear walls? Again, these shear walls should be symmetrically placed. If we will place these shear walls unsymmetrically, then there can be the twisting of the buildings. So you can place these shear walls symmetrically so that twisting can be avoided. We can provide the bracing in the steel structures, wood structures, and even the concrete structures. We can provide the dampers. They can absorb the energy, and damages can be reduced. We have these different types of the dampers: viscous dampers, friction dampers, and the yielding dampers. In the viscous damper is just like the piston. We have the fluid inside this piston. And friction dampers, they absorb the energy because of the friction between the different parts. And then we have the yielding dampers. At this portion, the dampers can yield and then they can absorb the energy. And how can we place the dampers? We normally place the dampers in the buildings along the bracings. So this is the viscous fluid damper, viscous fluid damper. This is the viscous spring damper. Friction dampers. And then this is the metallic dampers. So we can use different types of dampers to absorb the energy. One type of the damper is tuned mass damper. Tuned mass dampers is a device to reduce the amplitude of vibration. And one of the world's second largest scappers is equipped with the tuned mass damper in Tepai. And these are the specifications. And because of this damper, the vibration of this tall structure that was reduced from 30 to 40%. Then we have the base isolator. What are the base isolator? We can isolate the structures from the base. And the construction is, we have the rubber here, alternate layers of rubber, elastomeric rubber, and the steel plates. And this bearings, elastomeric bearing, they can take the building loads or the structure loads. They are very stiff in the vertical direction, but they can move in the lateral against the lateral loads. So structure will move as a whole and there will be no damage to the structure. I will show you one video and then you can see how the structure will behave during the earthquake when the base is isolated. You can see here during an earthquake, there will be the vibration of the structure, base is fixed, but when the base is isolated from the ground, then the structure will move as a whole. As a structure will move as a whole, there will be no vibration and there will be no damages. Our damages can be reduced because of these isolators. I can show you some videos now. Okay, look at here, the first video. In the first model, there is no damper. Look at the response. In the second video, second model, some damper is used. You can see these are the dampers, fluid dampers. And you can see the difference between the response of these two models. This model is vibrating more than this model. It means by using the dampers, we can reduce the vibration in the system. Look at another video. Maybe you cannot listen the voice. So I will upload these two videos in the course folder. This is the response of the structure or the non-structural components, furniture inside the building because of a certain earthquake. To reduce this, reduce the vibration, what we can do, we can isolate the structure. And these are the bearings. Try to understand this experiment. We have a room here with and without isolator. Look at the response. This is the shake table testing. We can see the response without isolator now. Or the non-structural component furniture is moving. Structure is the same, only we have provided the isolator here now, at the base of the structure. So you can see the building is moving as a whole. The other details you can see yourself. I will upload today. Okay, this one. This is important. We have the alternate layers of the rubber and the steel. That's why it's very stiff in the vertical direction, but flexible in the horizontal direction. Additionally, what we can use the lead rubber in the middle to increase the damping in the system. And these dampers we can use under the foundation. Maybe you have seen these kind of dampers, the bridges, they're commonly used. We have lead rubber bearing, we have elastomeric bearing, we have the simple pendulum bearing, friction pendulum bearing, sorry. Okay, I will upload this video. This is the end of your part of this part of the course. Now, if you have any question, you may ask. कोई question है बेटा आपका?